Okay, so I guess with the social one, with the physics one, you have this issue in quantum mechanics where you alter an experiment just by observing it. So I guess the one I would ask both is with the social interaction side. Do you think that it could change your data, the fact that you're observing these people, and that would make them behave in a certain way because than in actual reality when they're not being observed, because people kind of behave differently when people are watching them, for example. So I guess that would be kind of a way to link the quantum and the social side, I guess. And I guess the question would always is when you observe these complex reactions, is it an issue that one of the measurements is difficult because when you observe it, you change the dynamics of the experiment as well, fundamentally.
You want to go first? Or?
Sure. In social interaction, yes, it makes a difference to people's behavior when they know that they are being observed. So one of the biggest issues, and one of the things that we spend most time in planning our experiments is to try to ensure that people are as little conscious of themselves as possible. And this is sometimes, as you saw the picture, that it's if you're wearing a mocap suit and then a head boom mic and an eye tracking glasses, it can be quite difficult. You're looking like a totally ridiculous idiot and you're in a very funny space. What we try to do there is to we know it's a laboratory setting and we're never going to escape that, but we have a kind of a procedure of learning to move around in the space, learning to move in a suit, learning to just kind of joke around, play some games, play catch, all kinds of things to make people feel more comfortable. And there's actually quite a lot of time that we need to use quite a lot of time to kind of calibrate all the system, get all the microphones to work, get all the mocap things calibrated, etc. So that it's actually good that there's something for them to do instead of just sitting and waiting. So while we are preparing our equipment, they are preparing themselves by kind of immersing themselves into the situation or kind of trying to ignore that they are having all this gear. So it's a problem, but we are getting better at, I think, tackling it.
Yeah, so in physics, it's so in quantum mechanics there is the problem of measurement, but it actually applies mostly to very, very simple systems. So if you do a laboratory experiment with, say, an individual photon or an individual, ion, then you can have you can actually have the quantumness of the state to continue for a very long time, and then it actually measures when you measure something, because then the system collapses to a state. But what actually happens is that when you have a very complicated experiment, you have gazillions of particles going on, and actually the measurement that is meant in quantum mechanics isn't actually a person measuring. What happens is something called decoherence, where the system collapses into essentially a classical state very quickly. So it is an issue for people who are doing low energy, certain kind of, say, optical experiments, but for particle physics experiments, it's not an issue. It's also, we have to, the experiments are, there are a lot of unknown variables, so you have to have huge amounts of statistics. So each experiment is redone, I don't know, billions and billions of times. So, you have a lot of data, so that isn't a problem.
Okay. I think from what I understood from what you said is that this kind of, I guess it's kind of like, I would think of it as a transformation. You transform into one system, you do some calculations, it makes it easier, and then it gets you information about something in a more complex system. So you mentioned that this system is fundamentally difficult to measure and observe. How do you verify these theoretical calculations if fundamentally the system is difficult to measure in the first place? I guess is what I would ask. Because we always have this problem in my field, especially if you have a numerical model or you have some kind of simulation, is it always has to be compared to some extent with reality. But I guess the reality is difficult to measure in your case. So how do you verify or kind of benchmark these kind of?
Yeah, I hope I'm answering your question, because I started thinking about how complicated actually quantum mechanics is in this setup. But in principle, we're very far from understanding the theories that actually describe, say, nucleon collisions. So, for example, one of the maybe the biggest result of ADA-CFTs was that people actually computed that a relativistic fluid has a limit on viscosity, and then you go to a laboratory and measure viscosity of this fluid. So it's a very, our understanding of the systems is so crude that you're not really, if you can measure one thing and the number looks right about right, then that's a huge, achievement. So we're not yet in the state where you can actually sort of have loads of data and a lot of parameter fitting and so on. Of course, if you could do that, then that will be a problem. And hopefully we can do that in near future, because that would actually enable us to also learn something about the theory in a laboratory. I mean, there's also,
So it's a more qualitative and quantitative kind of.
Absolutely, we're really doing very qualitative things at this point. Time will tell whether it'll ever become a really quantitative thing.
I have a question for Tommy. When you do this laboratory experience with people, how do you invite them, and do you do them with large numbers of individuals and then generalize the results, or how does it work?
That depends on the experiment. Quite often it's the classical, usual getting people who are within the university community, so it's usually students. People willing to do something for a free movie ticket. And of course the opportunity to get cool selfies with the gear on. But more seriously, it's some of these experiments have larger kind of have larger N. So we try to accumulate more pairs or more participants, just so that we can see what the kind of limits of individual variability are. So there's a very big, of course, it's the behavior in these cases is more variable than it would be in individual settings. So that's one of the reasons why we try to get, like in the conversation paper, I think we have 13 pairs. So it's not huge, but it's already enough to see that there is some similarity, there's some kind of pattern going on. With this finger moving, we have a little bit more people. It's more classical experiment, so that's different. So the generalization is not necessarily always the intention. So it's not to say that this is how people work in this situation. It's more to, it's quite often, and for many of our measures, we do quite a lot of individual. So we show data for all different pairs, for instance, just to show that this is something that different pairs do very, very differently. And it's an interesting result if we see differences in the data rather than kind of neat averages that kind of stack nicely within condition. We did another. I'm now involved in a project in Paris where we do movement improvisation, and then we try to measure it by disturbing the improvisation as little as possible. So it's a little bit of a kind of a next step from what I just showed, and there it's people recruiting people who have some kind of dance background or some kind of an improvisation background, and they basically just come for the improvisation class, and then we do some measurements like on both sides of it and a little bit in between. So that's another approach. And then for the like the third final kind of way is that for the social emotions, when we had people rating these kind of animations, we were using the internet basically, just because we needed, and we got something like 300 different people rating our videos, and that would have been impossible like in a traditional way.
Well, I could ask one question. How do you land into or onto this type of areas of research? When did you know that this is the thing I really would like to do? Or why did it happen? Did you have some person who was really sort of big thing to follow, or just...
I can answer this first. So as I mentioned, I did my PhD in cosmology, and in cosmology, one of the most important theories is general relativity, because that's what describes how the early universe evolves. And when I moved to Germany to a postdoc, there was a group that was starting out doing research in ADA-CFT, but the problem was that these people had a background in nuclear physics. they had no understanding of how general relativity works. So they came to me and asked, we're trying to learn this new thing, can you come and teach us how to do this? And I started working on that, and soon found out that although I don't understand about the string theory or the particle physics that much about, I can carry out the relativity calculations and really sort of start making research on the field. So that's how I ended up doing this.
Yeah, I started as a musicologist, and I was mostly interested in cross-cultural cognition. So what's different between, let's say, the South African way of processing and understanding music and the Finnish way. And very quickly, when I started my PhD in Cambridge, I very quickly kind of narrowed it down to issues of interaction and doing things together rather than having kind of a very high individual skill. So I was kind of interested in looking for musical skills that would kind of vary between musical cultures. So there might be, let's say, more dexterity or kind of more accuracy in one musical culture because it kind of focuses on individual high-level training, and another one where the kind of being together would be more important, and that's where kind of things started to snowball. And then most recently, I've now been working in Aalto University. I was recruited by Riitta Hari to work on the brain-to-brain project, which was looking at two people's brains, and they wanted someone to help with the behavioral side. So I'm not a neuroscientist, but I already had some ideas and some methods and some tools to quantify entrainment and other kinds of people acting together, and that was what I then started doing there, and then new things.
So you studied the behaviour between two people, basically. So my question would be, how would your results change depending on if you did this experiment in different countries? Because it seems like people have these different social interactions. Some cultures are more expressive than others, where from experience in Finland, people are more kind of reserved, and maybe UK as well. Do you think you would have different results if you, for example, your dance experiment, if you go to a culture that is more expressive and more vocal compared to cultures that are more reserved, for example? Do you think that would have any kind of bearing on your results?
Yeah, that's one kind of source of variability. There are big differences in let's say how people behave in a conversation, or what's a comfortable distance from each other in an interaction situation like that. So that's one reason why in some of the studies, like for instance the conversation study, we use only Finnish people, not only for the language but also because they share quite a lot of the conventions of conversation. However, at least some of these studies, I would argue the mirror game and the kind of finger moving is trying to drill down to very basic behaviors and kind of very basic mechanisms of interaction that I would argue as mechanisms are universal, even though we might be using them in slightly differently in everyday life. But so that there is this kind of attempt, at least, to kind of not just look at the surface of interaction, but try to go into the mechanisms. And of course, that's most pronounced in the brain studies, where you then look at neural mechanisms. And to look at neural mechanisms, you need to go to very, very basic or very, very kind of reduced behaviors as well. And that's why even the finger mirror game that we've done in the 2MEG setup is a kind of even more reduced version of the mirror game that we just did. So I guess kind of two things, that there is variability in it that comes from nationality or comes from culture, and that's interesting as such at a level. But then mostly we are looking at mechanisms that are more universal.
Okay, thank you. I also have a question for Tommi. I was curious about if you could elaborate a bit more, if you have found some patterns of leadership in these social interaction games. Like how can you tell what happens when someone starts to lead? And if you can, what kind of general social impacts you could have with these findings?
That's a very good question. It's quite difficult to say. I would actually say this is not our study, but it's something that I cite all the time because I find it very interesting and I think it's extremely telling of what's going on. So there was a study by Werner Goebel and Carolyn Palmer in Vienna. They were studying pianists playing duets. So they had a kind of a soloist or a person who was playing the melody, like the more kind of higher tone, and they were given the leadership role, or the role of the leader. So they get the kind of more dominant role and also the instruction to be the leader, and the other person is supposed to accompany and follow and play the kind of lower part. And in that study, they showed exactly the same picture as we showed, that both are actually influencing each other. So it's something that you can have the role, you can have the instruction, but you still can't switch off this kind of mutual adaptation. So at the kind of lower behavioral level, things are more equal than they might be in this kind of world of roles and assignments. So I guess what the social implication might be is that there's mutuality and the kind of the basic mechanism works on the principle of equality much more often than the principle of hierarchy. And maybe that's
I have a question to you both, even though the key word is repeatability, but the nature of the question is a bit different to you. So with Olli, it would be that I can't remember anymore what is the thing which was the mess. But like it was complex thing to do. But can you, if you repeat the measurements, or can you even measure anything? So are the results the same? And then for you, is that if you would repeat or like make the same pair of people do the same, for example, the finger stuff, or like is there any sense for doing that? Is there too much learning, or like does it distort the picture what you're trying to find from there?
Right. So in heavy ion collisions, you take ions, which hopefully are all the same, and you collide them. But of course, it's completely impossible to directly, make the collisions head on. So what happens is you have huge bunches of ions and you collide them together, and then, every thousands or 10,000 times when these bunches cross each other, something happens. And usually when you have two ions and they don't collide head on, but they just sort of very weakly touch each other. And this is called the impact parameter, how far away they are when they collide. And of course, then what you do is you make this measurement billions and billions of times. And then you can average out this thing. You know that every time you have a different impact parameter, you will have different kind of results. But then when you just repeat this experiment enough times, you then get a distribution of how things happen as a function of, for example, this parameter. And this is something that in particle physics is very common, like also for example, in the experiments when they found the Higgs particle, you cannot tune the setup in such a way that something specific happens. You just collide a bunch of stuff and then you repeat this long enough that something interesting happens. It's like in a typical particle physics experiment, 99.99999% of the events are completely uninteresting and they're not even saved to hard disk. Everything else is they're just thrown away, and then you just hope that once you repeat the experiment for long enough, you get something interesting. So again, it's just a question of repeating you had 13 data points, we have terabytes and terabytes of information.
Yeah, so I think learning effect is something that necessarily happens. One way of trying to minimize that or make it not so significant is these games and what we do before we start measuring. So typically that entails some kinds of either directly practicing what they are supposed to be doing or there's something that's similar. Of course, there's always learning, and one could argue that you could take the data and then just look at how people learn to be together, or how people learn to get along with each other, or how people learn to interact with each other. That could be one way of studying this, and it would be maybe an interesting way of looking at things. But typically we tend to try to give people the chance to practice so that things would be relatively easy, and so they wouldn't need to learn as they are doing. They would just we use simple things that they already know. So I guess you all you didn't have much difficulty in doing this. You would probably get better at it when you train, but it's not a huge kind of thing. It's not like playing tennis or something. And then we use the kind of classical ways of minimizing learning effects in our effect, as you do in psychology, that you randomize the order of conditions between different pairs and these kinds of things. So we hopefully don't show order effects, but we show some other effects.
I could actually add something to this, that in physics I think there's the issue of theoretically can you repeat the experiment, and the answer is always yes. But there's the relevant question of can you practically ever repeat the experiment. For example, the Large Hadron Collider, which has found the Higgs and so on, has been responsible for many interesting physics results. It's completely improbable that somebody would build another machine like that. I mean, it is the most expensive piece of hardware that mankind has ever built. So there is this fundamental question that there is, in principle, only one device in the entire world that can actually produce this data. Is this, I mean, in principle, still it is repeatable, the experiment, but of course in practice it's not very probable, and that's why the experimentalists are very, very strict about their methods, so that the possibility of selecting, being hopeful and selecting good data is impossible. Everything is done in black boxes. The people who are looking at the data don't know whether they're looking at real data or simulated data and so on. But in principle, this is I think, a relevant, at least, if not physics question, then at least a relevant philosophical question, that what's the nature of the repeatability of the experiment.
In the duality, you are computing something in the classical gravitation theories, okay, but you have 3 space dimension, and the duality was up to 4. Yes. So how do you get rid of this finger?
So basically, what you do is that, for example, if you have, let's say you have 2 particles in the boundary field theory, there are 2 points in space-time, and then you ask, how does this particle go from this point to the other point? Then when you look at the dual picture, the GR picture, what actually happens is that there's a geodesic that falls into the bulk of the ADS space and comes back. So that's the way, at least, I think about it. It's qualitatively very difficult to think about. But basically, what you do is you compute an object in the relativity, and then you take the limit where it's far away from the center of curvature, the center of the ADS space. So somehow the intuitive picture is that you have a balloon, and the GR lives in the center of the balloon, and then the field theory lives in the boundary of the balloon. And because of information is conserved, somehow these 2 pictures are equivalent. I'm not sure if this answers your question, but this is the way I at least am able to think about this.
It's good that you are able.
Can I ask a question?
Yeah.
I have a question for you. So I find it very fascinating, like when you're comparing, let's say, string theory and how it's completely failed with your theory, which still has the wrong number of dimensions and it doesn't quite match with reality. I was wondering, what's the hierarchy of how bad your theory is, or how good your theory, like what makes 2 completely non-reality linked theories, right. What makes one of them better than the other?
Well, I think it's not how bad some theories is not a property of the theory itself. It's the property of the scientists who are dealing with the theory and what they claim they're able to do. So string theory is a beautiful theory. It works. It's a wonderful theory. It's one of the greatest scientific achievements of theoretical physics, but it just doesn't describe reality. Now, if you make the statement that it does describe reality, then it's a very bad theory. But if you only think of it as a mathematical tool, then it is a beautiful theory. And the same thing here. I mean, if you're claiming that ADS CFT is really, it describes reality one-on-one, it's a terrible theory. But if you just say that it is a one possible tool of computing something in a certain theory, and maybe we can learn some general lessons out of it, then I think it's a great tool.
So it's not just that it has its number of dimensions is
No.
closer to reality than.
Well, I mean,
ever.
string theory usually has 11 plus 1 dimensions. So in that sense, we're closer to reality. But I'm not sure that's the right way of classifying badness of theories.
So, from my understanding, this kind of links classical mechanics and quantum mechanics. How do you kind of get over this wave particle duality issue? Is that consistent? Is that contained in our mathematical description, or where you have things that behave both as a wave when you observe it, but when you actually measure something, actually it's actually a particle. How does that fit into this kind of?
Right. So that's a good question. I started during the last question. I actually started thinking what happens in the GR when you measure something. But I guess there's a technical answer, which is that the field theory is actually something we call large N limit, it means that it behaves more classically than your average quantum field theory, but that doesn't really answer your question. What I think the correct answer is that measurement is always something that comes from outside the system. Like somebody once said that quantum mechanics is completely deterministic as long as you don't measure anything. Which is a true statement. Like the way probability wave behaves according to a deterministic law of physics, and the same thing here. The gravity and the quantum field theory are completely corresponding as long as you don't measure anything. And then if you measure something, then that's a sort of not a hand of God, but a hand of a scientist coming from outside the theory, and then you have to insert that by hand. So the answer is that if you measure something in the boundary field theory and you change the state of the theory because of the measurement, then you will have to do the same by hand insertion of information into the general relativity.
You think it's borderline impossible to actually get theory and measurements actually to kind of?
No. What I'm basically just trying to say is that when you do a computation in quantum mechanics, of course, you don't carry out a computation for a specific measurement. What you do is you get a probability distribution, and then you make the measurement, you repeat it enough times, and then hopefully your data points fit the probability distribution. The same thing here. You can figure out that you have some process in the field theory, and then you do the computation in the GR, and as a result of this computation, you get a probability distribution.
It's like statistical mechanics.
Exactly. It's like statistical mechanics. Then you take this probability distribution, you go to the lab, and hope that your experiment fits the data.
So you
Sounds very clear.
So you're reproducing a probability distribution of the process. So if you repeat the experiment so many times, you'll be able to reproduce a probability, but not on a point-by-point basis.
That's exactly what's going on, and that's exactly what's going on in actually. This statement has nothing to do with ADS-CFT. This is in all of higher energy physics. You do these computations that are happening in quantum field theory, but you get out probability distributions, and then you go and measure those. And then if you actually want to start thinking about what actually measurement means, then you have to go to a very different field of physics, because that means that you will have to have large, coherent, low temperature systems and so on. So that is also an active field of research, but it's not very much related to high energy physics.
You can decide to which you can answer. There are either the great big question, which would be the classical one, that what is the good for the humanity for all this, and then the last question was that, like, can you really make your own black holes? Maybe I can answer both.
Can you make your own black hole? Sure. And with a pen and paper, you can. You take pressureless stuff, and then you wait an eternity, and they will form a black hole. On a pen and paper, it's not a problem. In a laboratory, it's impossible. In fact, there's a theoretical sort of result which tells you that an outside observer can never see a black hole form, because the time slows down near the future black hole so much that you will never be able to see it form. Whereas if you're located at the place where the black hole will form, then it takes just a finite amount of time. But on pen and paper, it's not a big. It's something that a second year theoretical physics student can do. And the first question then, how does this benefit humanity? I don't know. It keeps theoretical physicist out of harm's way. I know. I mean, this is theory that, quantum gravity can, in many ways, can be considered to be the holy grail of science in general. There are always people who say that, well, you can't know what the implications are before you actually know what the theory is. That's true. Maybe there is some crazy way of once you know the theory of quantum gravity to take advantage of it and make a faster car with it. But in practice, it's completely impossible. I think we're talking about so strange energy scales that they're not really just relevant for everyday life. But that same thing applies to, I think, all of high energy physics. I think the last time, I think the biggest outcome of high energy physics was the invention of World Wide Web, which was invented so that you could share, the particle physicists could share information about their experiments. So, I think it's intellectually dishonest to claim that maybe there will be some huge practical outcome. But this is basic science. We're asking questions about what reality fundamentally is, why there is such a thing as time, why did the universe, why it exists in this first place, why there is visible structure in the universe. These are good questions, but I mean, if you're asking, of course, then you have to define what is actually a benefit for humanity. If just knowledge is, then, well, the possible benefit is huge. If you only talk about, increased GDP, then not very much.
Okay, so you study what the universe is and how it's formed and all that, and I think our studies are linked to what humanity is and what it is to be human. I think it's fundamentally, to be human is fundamentally to be social. To be human is fundamentally to be playful, to be artistic, to play games and to make art. And I think, on a really practical level, the types of applications for our research, we've already applied some of this to research on music therapy, with therapy with children with communication difficulties such as autism. So there's a relatively direct application of understanding how healthy human interaction mechanisms work to what happens and what can we do to them if they for some reason don't work. And I think more generally the type of work, and especially the social emotions project, has as its kind of ideological background the idea that we want to learn more about empathy, and we need to learn more about human emotions, and we need to talk more about empathy, we need to talk more about emotions, and not just on a kind of fluffy level, but on a more kind of solid, scientifically founded level. And so I guess at least what drives me to some degree is that it's helping us understand who we are, and the more that I understand is kind of reinforcing my view that, not a very scientific way of putting it, but it's reinforcing my view that humans are social and emotional beings.
Well, you didn't answer the black hole part. See, I mean, what do you think? I mean, in human mind, are there sort of black areas where you can't penetrate?
That's a good question. Yes, I think we talk a lot, especially in neuroscience, there's a field of neuroscience that's been dubbed mind reading. So it's basically trying to decode from the brain signal what the person has been thinking about. Usually whether they are thinking about the red ball or a horse. So it's not a very, very kind of sharp instrument yet. But in that case, I would say that there is always a private me. There's always something in my mind that you can't read, no matter how good we are playing this thing together or whatever emotional interaction we have. There's always this private part of our mind that can't be read by an MRI or a skilled other individual or any researcher. So in that case, it doesn't have to be a black hole. It can be a very shiny and bright sun. Sometimes a red dwarf, sometimes a giant, but it's something private.
Thank you very much for this white holes. We close this and thank the speaker and discussants.